Hi everyone, I hope everyone is doing well. Okay, so in this section we are going to tackle 9.2. We're going to start graphing polar equations. So first and foremost, to graph a polar equation, what we have to do is we have to refer to the graphs of corresponding equations in the Cartesian coordinate plane, which we can do because we've done chapter 4. So when we were graphing, y equals sine x, cosine x, and so on, all of that stuff we're going to have to recall right over here. Okay, the one difference is, whereas before we were graphing on the xy axes, so we were looking at the change in x with respect to y. Now we want to look at how the radius changes from the origin with respect to theta. Okay, well, let's just, dive right into it. The first shape we're going to graph are circles. All right, so just like in the xy coordinate plane, we have, you can graph a linear equation, you can graph a parabola, you can graph a quadratic equation, a quartic equation, and so on. And each of them have their own equation. So, for example, a linear graph has to look like y equals mx plus b. It's the same thing in the world of polar coordinates. Different shapes have their own form of equations. Circles have polar equations of the form r equals a cosine theta or r equals a sine theta to produce graphs. So for example, if I have r equals 5 sine theta, I know just by looking at it that that's going to be a circle. Okay. Well, you know what? Let's do one. So I want to graph y equals 3 cosine theta, but you know what? First I'm going to graph y equals 3 cosine x, just like we did in chapter 4. All right? So we know that cosine starts at the maximum, and in this case the amplitude is 3, so it's going to start here. Then at pi over 2 it's going to go to 0. At pi it's going to go to the minimum, then 0, then back to the maximum. And then when I graph this, let's see how it looks. Oops, not like that. When I graph this, when I connect those points, that's how cosine looks, right? Okay, so let's take a look at this graph a little bit more closely and see if we can see any trends and how this graph is behaving, because we're going to look at some different things now that we didn't before. So first and foremost, when theta is 0, the graph is farthest from the x-axis, right? You see that? The graph is farthest from the x-axis when theta is 0. Now, as we approach theta equals pi over 2, and I'm just going to change this to pi over 2. As we approach theta equals pi over 2, what's happening to the graph? The graph is approaching the x-axis, right? And the distance between the x-axis and the graph approaches 0. After this, the graph now goes further away from the x-axis until we approach how much is this? Pi, where it's farthest but on the opposite side. And then when you approach 2 pi, right, then it gets closer to the x-axis, and then as you approach 2 pi, it goes farthest again to the maximum. So again, it starts far from the x-axis, gets close, gets far again, gets close, gets far again. That's what we need to look at, right? Okay, and so keeping that in mind, now we're going to graph y equals 3 cosine theta in the polar coordinate plane. And what I have here is a chart, and we're going to just pick values and we're going to put in our values, and you're going to use your calculator to do that. Just in the home screen, in calculator mode, make sure you're in radian, all right? So we know that in this case, r equals 3 cosine 0, well, that's just 3. Then at pi over 6, it's 2.6. And if you want to go to the graph that we just graphed up here, the xy coordinate plane, so this one here is pi over 4. And so pi over 6 is here, and then pi over 3 is here, right? And then it's pi over 2. So that point right now, pi over 6 comma 2.6, that's right about there, right? Pi over 6 comma 2.6. Okay, so next I have pi over 3, and at pi over 3 my function is 1.5. So pi over 3 you can see here, right? Pi over 3 is 1.5. So do you see how we're basically, just, tacking on those points into this graph here. At pi over 2, r equals 0. At 2 pi over 3, right? 2 pi over 3 is now here. We are at negative 1.5. So 2 pi over 3 is right over here. Okay, just to give you some perspective. So this is 2 pi over 3, and the point is 2 pi over 3, negative 1.5. So we're right there. And then at 5 pi over 6, it's negative 2.6. And then at pi, right, it's negative 3. Then 7 pi over 6, now we're here. Okay, 7 pi over 6, it's going to go back up again, right? It's going to go back up. So right? You know that you're just going to traverse through the same point. So you don't even have to plug it into the calculator anymore. Because at 7 pi over 6, it's going to be negative 2.6 again. Then at 4 pi over 3, it's going to be the same as this one, negative 1.5. Then at 3 pi over 2, it's 0. Then it's going to be 1.5, 2.6, finally reaching 3. Okay? All right. So let's go back and think about when we start with 0 radian, when theta is 0, the graph is farthest away from the x-axis. Okay, so farthest from x-axis means farthest from the pole in our new graph. Right? Farthest from the pole. So let's go over here. Where is the pole? Here is the pole. So when theta equals 0, if I was farthest from the x-axis, now I'm farthest from the pole. That means I have the biggest radius. All right? So when theta equals 0, r is equal to 3. And where is 3? 1, 2, 3, right there. Okay. Now, so that's the biggest radius over there. Okay, when theta equals pi over 6, I'm at 2.6. So 1, 2, 2.6 is right there. When theta equals pi over 3, we're at 1.5. When theta equals pi over 2, we're at 0 right there. So take a look at what happened for a minute. Remember how the graph was farthest away from the x-axis? Then it got closer, closer, closer. Well, look, farthest from the pole, biggest radius, then closer, smaller radius, closer, smaller radius, and then finally the radius is 0. Okay, moving on. Pi over 2 is 0. Okay, so 2 pi over 3, that's 2 pi over 3. I'm at negative 1.5, so the opposite side right there. Okay. 5 pi over 6, that's 5 pi over 6. I'm at negative 2.6, so on the opposite side, negative 2.6 right here. And then at pi, I'm at negative 3, pi negative 3, so I'm right at that first point. Okay, so let's just see what happens. Let's just trace this, shall we? Tracing from the first point we graphed to the last point we graphed. What is the trajectory? There is the trajectory. And hey, what shape does that make? Oh my God, a circle. But what do you notice? Right around here, right here, the circle ends. Okay, so then where is the other points? Where are the other points? Well, at 7 pi over 6, I'm at negative 2.6, right? Negative 2.6, so right there. And then at 4 pi over 3, negative 1.5, right there. And at 3 pi over 2, right there. So what do you see is happening? You are retracing the circle, okay? Now, do you have to do it twice? Of course not, right? Once you traverse one circle, you're good to go, and then, you can stop. So, congratulations, you have just graphed your very first circle in polar coordinates. Okay, now let's remind ourselves what the equation here was. It was y equals 3 cosine theta. Okay, now what's the diameter of this circle? What is the length from here to here? That's 1, 2, 3. Oh my God, where have we seen that before? Oh, that number. That's where we've seen it before. So if my equation has the form y equals a cosine theta, then a, okay, absolute value, because it could be positive or negative, is the diameter. Okay, so what does it mean then if I had r equals negative 3 cosine theta? Well, negative 3 means it would just have been graphed on the negative side of the polar equation axes. Okay, all right. Now we know that cosine starts at the maximum, so we know that when we're graphing y equals 3 cosine theta, and when theta is 0, cosine is a maximum. That means when theta is 0, it's going to start, farthest away here, right? So if we come down here, look at this. When I have a cosine theta, that's what that looks. Negative a cosine theta, I have it on the opposite side. But when I have a sine theta, now when is a sine theta is equal to 1? When is sine theta equal to 1? At pi over 2, right? So that's why sine of theta is on the vertical axis, sort of, at pi over 2, right? Because sine of theta is maximum at pi over 2. And then if I have negative sine theta, then it's on the bottom side. All right, so that's how we graph circles. Okay, we're going to graph one more thing and call it a day for today. Okay, so we did circles. The next level is limicins and cardioids. All right, that's a funny little accent mark there. So this is the C, and then that is a French accent. It's called the CD, and when you have that letter C, that accent changes it from a K sound to a S sound. So that's a limicin, and then we're going to graph cardioids. All right, so the equations for limicins and cardioids have the form A plus or minus B cosine theta, or A plus or minus B sine theta. So for example, if you have r is equal to 3 plus, 2 cosine theta, okay? That's what we're looking for. Now, A and B must be positive, okay? I'm sorry, if A and B are positives, you create a limicin, okay? Which we're going to go over next time, but a limicin is when a circle rolls around the outside of another circle. What does that mean? We'll talk about it tomorrow. Now, so when you see an equation like this, right? This equation for a minute. Oh, I erased it. I didn't mean to erase it. So when you have, let's say, 3 plus 2 cosine theta. So here is A and here is B. And you can see that A and B can either be equal to each other, or A can be bigger, or A can be smaller, right? The case where A and B are equal to each other is called a cardioid. Why cardioid? You will see right now. All right, so we're going to do all three cases, and sure enough, the first one is when A is equal to B. So for example, I have y equals 3 plus 3 cosine theta, and you see that these two numbers are the same. All right, so we're going to graph them in both Cartesian and polar coordinates, okay? All right, so first of all, when theta equals 0, right? When theta equals 0, we're going to get r is equal to 3 plus 3 cosine 0, right? Just to get an idea what we're looking at. Cosine 0 is 1, so this is 3 plus 3, so that's equal to 6, right? Again, this is cosine. When theta equals 0, cosine is a maximum, and that's our maximum value right now, is a 6. Okay, so let's plug in pi over 6 in the calculator. 3 plus 3 cosine pi over 6, we get 5.6. Pi over 3 gives us 4.5. Pi over 2 is when cosine of theta is 0, so we just get 3. 2 pi over 3 is 1.5, 0.4. And then what about cosine, 3 plus 3 cosine of pi? Well, cosine of pi is -1. And then, so all that gives you 0. And then we get 0.4, 1.5, 3, 4.5, 5.6, and 6. Now, so I just did that for completeness. When I'm graphing it on the x and y coordinate plane, I can actually do it without that chart, right? Because, okay, so what is this? This is 3 cosine theta, amplitude of 3, but it also has a vertical shift of 3, right? Vertical shift of 3 and amplitude of 3. So 1, 2, 3, okay? I go up, then 0, then 1, 2, 3 down, then to the center, then up. That's how we always graphed, right? And here too, that's how we're going to graph it. Okay, so let's take a look at these trends, right? Far from the x-axis, close to the x-axis, and so on. That is a horrible looking cosine. Oh my gosh. Okay, that's fine. We're going to deal with this one. All right, so when theta equals 0, the graph is farthest from the x-axis, okay? As we approach pi, the graph comes down, down, down to the x-axis. Then it goes away from the x-axis back to 6. Okay? So right here, it becomes 0, and then it goes back until when we get to 2 pi. All right, so let's just graph that here. Okay? So in this case, if we have to go out 6 units, we need to recalibrate this. So we're going to make this 2, 4, 6, 8. Okay. When theta is 0, we're at a 6. Yes, there is some eyeballing involved here, okay? All right, so when theta is pi over 6, I'm in the chart now. I'm at 5.6 right here. Pi over 3, I'm at 4.5. 2, 4, 4.5. Pi over 2, I'm at 3. 2 pi over 3, 1.5, so now we're on the inside here. 5 pi over 6, we're at 0.4, super close to the 0. And then at pi, 0. Okay, so what have I traced so far? What have I made so far? That's what I've made so far. All right, so now, so look at that. My radius was largest, and then it got smaller, 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 smaller until it became 0. All right, so now let's continue. Let's continue. Now the radius is going to get big again, right? So at 7 pi over 6, we're at 0.4. At 4 pi over 3, we're at 1.5. At 3 pi over 2, we're at 3. At 5 pi over 3, we're at 4.5. At 11 pi over 6, we're at 5.6. And then we're at 6. So from here, we're going to go back out, 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 and there. And now, what shape is that? Hey, does that look like a heart? Oh my God, it totally does look like a sideways heart. Oh, wait a minute. Is that why it's called a cardioid? Because cardio means heart? Oh my goodness. Okay, so look at that. So those are cardioids. So when do we get cardioids? When it's y equals a plus b cosine theta, and a is equal to b. Okay, all right. I'm actually going to stop here today, but before that, I have a wonderful little thing to show you guys. This is something that I had gotten from a calculator conference 2 years ago in San Antonio. So here we go. Look at this. And I wish, we were there together. I was going to like give you all these files with the hats. Like through the hats, I was going to transfer them over, but one day. Okay, so polar graphs in the form of a plus b cosine theta when a is equal to b. Let's see. Okay, so look at that one. It's the same exact equation that we graphed. 3 plus 3 cosine x. You see how it goes up to 6, down to 0, up to 6. They did it in degrees. We do it in radian because we're better than them. And so look at what's going to happen. As we traverse this curve, we are going to graph a polar form of it here. So watch both of them at the same time. All right, ready, set, go. All right, look. Biggest radius. Radius gets smaller, 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 smaller. And radius is at 0. Okay, and now the radius is going to get bigger again. Bigger, bigger, bigger. You see the radius. You see how the radius is getting bigger? And there you have it. You've got your cardioid, right? And we can go, over and over and over again, and you can see that, right? You could just do it all day long. So you could just, keep playing that part of the video over and over and over again. And if that doesn't calm your nerves, I don't know what will. And with that, okay, I'm going to leave you for today, and we will see each other again tomorrow.